In this presentation, I'm going to talk about the tsunami hazard from a number of rupture scenarios in Cascadia. Um, Most of the studies about these tsunami scenarios from these variety of ruptures, be it from a probabilistic standpoint or from a deterministic approach, usually compare what they have in terms of coastal tsunami amplitudes to what they get from the quote-unquote worst case tsunami scenario, which they calculate from a lower magnitude 9 rupture as determined from paleoseismic data. Now the question is, does this rupture necessarily correspond to the worst case tsunami scenario? And also, what are the most hazardous segments of the Cascadia rupture in terms of generating larger tsunami hazard? In terms of rupture scenarios, I mean, we use all of these, as you know, for the initial condition of our tsunami simulations. And the first pass on doing this is using these things called locking models, which are basically calculated from the deformation on land and sort of extrapolated with some mathematical tricks to offshore. And this is, in other words, this is basically just the number of strain accumulated offshore that could be interpreted as the slip potential in terms of a rupture. And this particular kind of model is taken from Gina Schmansley's paper in 2014. And here I am showing the, I've selected this model because it's creating the largest amount of displacement right off the trench. And then I can use this in order to produce smaller sources. I can use a slip model, slip field, to and apply some scaling equations, earthquake scaling equations, to downscale basically the slip field, and to whatever lower limit that I want to. Here, for example, for magnitude 8, this doesn't really mean that the rupture, this entire planar interface will rupture to magnitude 8. What it means is that the rupture starts from if I start the rupture, for example, from a red star here as the epicenter, and I propagate the rupture southward, it'll use the slip values in this field, and I will accumulate a slip until I reach the magnitude cutoff, magnitude 8, and I'll have to stop there. And then I can move around the epicenter to wherever I choose in order to produce a maximum, another slip, earthquake slip scenario. This is an example of all of this. For magnitude 9, if I start to rupture at this little dot here in the north and I propagate it southward, at this point I reach the magnitude cutoff threshold and I stop. And then I repeat this process by moving around the epicenter, and this will result in a number of rupture scenarios for magnitude 9 in Cascadia. Then obviously I can keep playing this game for all other magnitude thresholds and build a data set of rupture. Remember, I'm not dealing with the time domain probability of the ruptures. This is from a deterministic point of view. Now I can, since I'm working with the rupture surface area, the catalog that I'm building is going to be Gutenberg and Richter like, and the distribution has a b-value close to 1. Now, I can use these surface deformations to produce tsunami simulations, and these tsunami simulations are the maps that you can see here are cumulative fields of maximum tsunami amplitudes across all of the rupture scenarios in any given magnitude threshold. So, for example, here in the left, I have the magnitude of magnitude 8 rupture, and I'm increasing the tsunami, the magnitudes to the right. Now, interesting features in all of this is that, well, local amplitude peaks do exist in central latitudes in the absence of irregular bathymetry. Cascadia is known for having more or less uniform bathymetric slopes as you approach the coastline, with a couple of exceptions. And of course, magnitude 9, if you look closely, is not terribly different from what you see in magnitude 9.2. In fact, I can quantify this using this MT metric, which basically compares two figures of the same grid to one another. And for two identical grids, MT would be equal to 0, and the larger the difference between the two figures, the larger the value of MT will be. And here I'm comparing all of these panels to the magnitude 9, M9.2. And as you can see, after magnitude 9, everything is pretty much the same because there is not much variation in MT, and the MT values are actually going to be very small, which means that magnitude 9 is a good representation of the tsunami that you will get from a magnitude 9.2. I can do pretty much the same thing to the coastal amplitudes. Here I have just flipped the map from the previous slides to its side, and on the bottom panels of the mesh that you can see here is the rupture potential, and here on top I'm showing the coastal tsunami amplitude profile. And in both panels here, the solid black curves are maximum coastal tsunami amplitudes from magnitude 9.2 earthquake. Now here I am simulating ruptures for magnitude 7.5 and 8, and the results are color coded according to the tsunami, the epicenter, the latitude of the epicenter of that potential rupture. For example, here, blue curves correspond to ruptures that originate from here, and red curves correspond to ruptures that start from lower latitudes. And I can keep playing this game, and again, magnitude 8.5 and 9, an interesting feature shows up, and that is that for ruptures that start from the north, the tsunami from those ruptures are more localized. Whereas if I do this on the opposite end of the rupture, the tsunamis, the large amplitudes are going to be widespread in a wider range of latitude. And the same thing happens at a magnitude 9. In fact, for a magnitude 9, the interesting features is that in higher latitudes, I'm almost saturating the limit from magnitude 9.2, and about 90% of those amplitudes are recreated. And if I moved the epicenter further south, I get a wider range of large amplitudes at almost about 90 degrees of the magnitude of amplitudes of tsunami from magnitude 9.2. And this is interesting because we're dealing with something in the realm of 20 meters, and 20 meters plus or minus 2 meters is probably not really that important in terms of hazard assessment. And again, for magnitude 9.1, I'm almost saturated magnitude 9.2 everywhere. And another important point is that the maximum tsunami amplitudes do occur at a central location here near along the coast of Oregon. Now, what are the contributing factors to all of this? Well, number one, obviously, is the scaling factor, scaling equation. The scaling equation that they use to get from magnitude to slip is very important. Here on the left, I'm showing what I showed you for magnitude 8.5 before, the exact same plot. On the right, I'm using a different set of scaling equations from Thing by Jum et al. In 2016. And as you can see, obviously, the tsunami amplitude is much, much smaller. If you just look at the vertical axis here on the left. But on the right here, on this map, I'm just superimposing the maximum tsunami amplitude from the original set of scaling equations that they used the work of Bob Giller back in 1976. And you can see the pattern of these two are very, very similar. Of course, the amplitude is very different, but the pattern of these two are very similar in terms of the geographic distribution of maximum runouts. Now, the second factor is obviously the choice of locking model, choice of rupture model. Remember, I told you that I used Gina Schmazli's, a specific form of Gina Schmazli's locking model. And the question is, what happens if I change the locking model with something different? And here to study this, here on all of these three figures on the right panel belongs to the same thing, that the one that I showed you before, Gina's model, and the one on the left here, the left panel is a simplified version of George Priest's model from the 2010 study, and in the middle, I'm using a dynamic rupture as the initial condition of the simulations. Here, I'm just basically introducing some noise into the locking model that I originally used. I'm calling it a randomized version. And in each case, I can go ahead and simulate the tsunami. As you can see here, tsunamis are, these are obviously very obviously different, but what I would like you to note is that the difference is mostly in the far field here. What about the near field? They seem to be pretty much very similar in the near field. And in fact, if you look at the coastal tsunami amplitudes, this is actually the case. Here in the left, I can see that there is a correlation coefficient larger than 0.9. And the two geographic series are very, very similar. There are differences in amplitude, and same thing is happening here. The difference is this guy here, that I am underestimating the coastal tsunami amplitude by a lot. And this is because I am removing the large scale features. I'm removing the long wavelengths from this otherwise really, really large front of the formation. And what all of this means is that as long as I'm not removing, I'm not losing a major feature in bathymetry, the near field tsunami amplitudes, the near field coastal amplitudes, it's not really a function of the choice of your rupture model. What about the rupture directivity? We've known now for a little while that rupture directivity, rupture kind of kinematics, doesn't really matter in the near field, and this is just a demonstration of the same idea. Here I'm using in a numerical experiment, I'm using a flat ocean and a concave morphology, sort of to mimic Cascadia, and here I have the deformation front. I just break these chunks in different patterns, and what I get is this kind of maximum tsunami amplitude simulation. And if I look at the coastal amplitudes, this is the result. And you can see in all of these panels, the black line represents the isostatic movement. Everything moves at sort of a static rupture, which is customary in some of the tsunami business. But then the colored pattern, I'm just changing the speed of the rupture, the direction of the rupture, and you can see the difference is not significant. The only two examples of difference are these guys, where I'm using a very, very narrow rupture. If you just go back here, you see that the rupture is very narrow, and this could either be due to the lack of coherent constructive pattern of the rupture building, or it could just be a numerical artifact from my simulation. So effects of rupture directivity are not significant in the near field either. And finally, what about the morphology of the coastline? If I use a concave coastline, what do I get? This is a simple numerical experiment. Here I have a flat, deep ocean, which is next to a shallow, narrow continental shelf, and it's by the coastline. I can approximate the curvature of this coastline by a large geographic circle, and as I decrease the radius of the circle, I'm going to be increasing the curvature of the coastline. And at each step of this simple model, I can simulate the tsunami and calculate the coastal tsunami amplitudes from this sort of a rupture that I have here, and here is the result. At each step, you can see, so the vertical bars here, the coastline, correspond to the coastal tsunami amplitudes. And as you can see, as I'm increasing the curvature of the coastline, I'm also increasing the coastal tsunami amplitude by roughly about 10 to 15%. So the curvature can increase coastal amplitude by about 10% through the focusing of the energy of the edge waves, because I'm just narrowing, sort of narrowing down the modes of the edge waves into one single geographic location. Now, what about tsunami hazard from all of this? From all of these simulations, I can calculate or count the number of cases, the number of simulation sites for which the tsunami amplitude, the maximum tsunami amplitude, exceeds 50% of what we expect from magnitude 9.2. Here are 12 sites. I mean, I have these funny locations, Portland and Astoria, even though they're nowhere near the coastline, but I'm just representing these points by their latitude. And these points are actually on the coastline. So this is just the labeling thing. And then here, as you can see, I'm plotting the 50% exceedance number as a function of magnitude. So what you can see here, with the exception of these three, everything else after about 8.7, 8.8, I'm reproducing at least 50% of the maximum amplitudes in 90% of the sites, which means that what I can do here, I can use this information in order to sort of bring down the preparedness threshold. So finally, the magnitude 9.2 rupture is not necessarily the worst case tsunami scenario. Several other smaller scenarios produce comparable coastal tsunami amplitudes. Near field effects of Cascadia tsunamis are not very sensitive, about just 10% to the choice of rocking model, as long as the larger scale features are preserved. Ruptures with hypocenters at the central segments make largest tsunami scenarios. And finally, concave morphology of Cascadia coastline focuses the tsunami energy in the central subduction zone. Thank you.